before we look at our two special forms, we're going to talk about what are called conjugates. So if we have a binomial, the conjugate's formed by taking the sign in between our two terms and switching it to the opposite sign. So, for example, the conjugate of this one, well, we could write down our terms and then switch the sign in between them. So this is the pattern that we use if we want to create what are called the conjugate of a binomial. Just write down your two terms and switch the sign in between your two terms. The first special form we're going to look at is called a difference of squares. Now, I want to help you understand why we factor the way that we do. So we're going to work with our conjugate pairs, a plus b, a minus b, and we're going to use the distributive property to expand this out. So we could distribute the a plus b to our first term, which is a, and then we'll keep our sign and we'll distribute our a plus b to our second term, which is b. We'll do a couple more distributions here. We'll distribute the a through to get a squared plus ab. Now we have to be careful here because we're actually distributing minus b into both of our terms. So minus b times a gives us negative ab, and minus b times b gives us negative b squared. Now notice that in the middle here, our two terms are going to cancel and we're left with a squared minus b squared. So this expression here is usually called a difference of squares. So if we ever encounter what we call a difference of squares, where we have something squared minus another thing squared, we know how to work backwards. We will factor it into its conjugate pairs. Let's work on factoring a couple difference of squares so you can get the hang of what it looks like to create your conjugate pairs. Let's start nice and small with x squared minus 9. Now if you notice, we have our first term is squared, we have a subtraction sign in between our two terms, and our second term is also squared. Remember that 9 is equal to 3 squared. So when we go to create our conjugate pairs, x must fill the first two spaces. One of the pairs is going to have a positive sign in between the terms, the other one's going to have a negative sign in between the terms. And because 9 is 3 squared, it's going to be the number 3 that fills our second two spaces. Let's move over to our next one. We have x squared minus 49. So in this case, we just need to note that 49 is equal to 7 squared, and so 7 is going to be the term that goes into our second slots. So we know that x goes into our first slots, we have a plus and a minus, and then 7 is going to go into our second spaces. Let's move down here to our third, 36x squared minus 1. This one's a bit more challenging, so I'm just going to rewrite this a little bit. So 36 we can write as 6 squared, and 1 is equal to 1 squared. So we could, if you want, factor out this power of 2. And now maybe it's a bit easier to see what your conjugate pairs should be. So what we have is we have 6 times x squared minus 1 squared. So now we know that 6x must go into our first slots. We have 1 positive, 1 negative sign, and then the number 1 must go into the second spaces. In our last example, we have y to the power of 4 minus 81. Remember that 81 is equal to 9 squared. Now, y to the power of 4, we can write this as y squared squared. So this tells us if we go to make our conjugate pairs, we should get y squared plus 9 and y squared minus 9. But we're not quite done yet. In our first binomial factor, we have y squared plus 9. This is a sum of two squares, not a difference of two squares. So there's no way that we can factor this one any further than what it is right now. However, take a look at that second binomial factor. This is y squared minus 9. So we have y squared minus 3 squared. This is a difference of squares. So we can go ahead and factor this one more time into conjugate pairs. Y plus 3, y minus 3. Next, I want to talk about binomials squared. Now, a binomial squared is anything of the form a plus b, all to the power of 2. So, some examples might look like x plus 1 to the power of 2, or 3y minus 7, all to the power of 2. So in order for us to have a binomial squared, we have to have two terms, and the power of our binomial must be 2. Now you might wonder why we care so much about binomials squared, so I'm going to go ahead and I'm going to expand out a plus b to the power of 2. Remember that the power means repeated multiplication, so we can think of this as a plus b times a plus b. Then we can use the distributive property. So I'll distribute a plus b to the letter a, and then I'll distribute a plus b to the letter b. And if we use the distributive property one more time, we'll get a squared plus ab plus ab plus b squared. And we have two middle terms that we can add together to get 2ab. Now it turns out this special result that we get at the very end has a special name that we call a perfect square. The reason we call it a perfect square is because this particular trinomial, we can factor it like so, and it becomes something squared. Our perfect square becomes a binomial squared. So using the distributive property on our binomial squared, we get a special form that we call a perfect square. This means if you ever see anything of this form, a squared plus 2ab plus b squared, you can immediately factor it into a binomial squared, a plus b, all to the power of 2. Now, one of the nice things about a perfect square is because sometimes they're hard to see right away, you can always use other techniques. So we could always try to factor this trinomial using trial factors or using the grouping technique. That will always work for our perfect square. However, if you do get really good at noticing the form of the perfect square, then it's much faster to immediately go from here and jump to our final answer of a plus b, all to the power of 2. So if you can recognize the form, it does tend to save you a lot of time when you're factoring expressions. So let's work on factoring a couple perfect square trinomials, so you can get an idea of the thought process that will go through my head as I'm working through these kinds of factoring questions. Now for me, I don't usually think about perfect square trinomials until I notice that my first term is something squared, and my last term is also something squared. So this is usually the indicator to me that I might be working with a perfect square trinomial. In this case, we get our value of a, so our value of a must be equal to x, and our value of b we also get, our value of b must be equal to 6. And we can use these values to try to see if they line up with our middle term. So our middle term of negative 12x must be of the form 2 times a times b. So what do we get when we multiply a and b together? Well, we get 2 times x times 6, which is 12x. So in these cases, when you differ by a negative sign, it's because this 36, or your last term, is actually negative 6 squared. So if I were to put a negative sign in here and switch this to negative 6, then everything matches up perfectly fine. And this means we have a perfect square trinomial, and we can factor it into a binomial squared, where a is equal to x, and b is actually equal to negative 6. Let's take a look at one more example. Again, I probably wouldn't notice that this is a perfect square trinomial until I looked at my first and last terms. So my first term is 2y all squared, and my last term is 9 squared. So this is usually when I start thinking, oh, maybe I have a perfect square trinomial. Now the same thing's going to happen to us that happened to us in that first example. So I'm going to switch 9 to a negative 9 right away, and that's because my middle term is negative. So what do we have for a? Right now we have a is equal to 2y, and b is equal to negative 9. At least these are our possible values. So let's see if negative 36 is equal to 2 times a times b. So 2 times 2y times negative 9. 9 times 2 is 18, and 18 times 2 is 36. So yes, we do get 36y, so everything checks out for our middle term. So this means we can go ahead and factor this right away into 2y, which is a, minus 9, that's b, all to the power of 2. Alright, my little epsilons, stay positive.